Let's talk about how we get the mechanical advantage of levers. Now, Trent, you know that you've been reading along here. You know that there are three classes of levers: first class, second class, third class. And it turns out you pretty much you use the same technique to calculate the mechanical advantage of all three. And as we go through that, hopefully you'll see that. So here we have in front of you a first class lever. A first class lever will have an effort on one side of the fulcrum and the load on the other side, and that's what we have here. Now, terminology, the words we choose to use. I tend to use a little bit different terminology, little different words. I think of this as the input side of the machine, and this is the output side of the machine. And everything I think that happens on this side I call it input, and everything on this side, I think of it as output. So I'm going to say that when you push down with this force, I'm going to say that is Fin. And the force that you want to come out, which is called, other places call it the resistance, I'm going to call that F out, okay? And that it's just, I'm doing it the same way everybody else does. Okay, so how do you get mechanical advantage? We need to identify, okay, mechanical advantage, it is the ratio of the force that comes out divided by the force that comes in. But I don't know those. In fact, I want to predict those. So what I need to do is use the technique of taking the ratio of D in over D out. So how do I get D in and how do I get D out? Let me go ahead and erase some of this stuff so that it looks kind of less. So basically, we've already talked about the effort, resistance. I use the term output force. We already know all this. Okay, enough of that, enough erasing. Okay, because basically I just want to make that clean so we can see it. What you need to do is find your fulcrum. So for all three classes of lever, it's the same thing. Find the fulcrum. Then, what is D in? D in is the distance from where you apply your input force to the fulcrum. So this is D in. That is the input distance. What is the output distance? You can probably already guess. You're going to figure out where the force is coming out of your lever. That's going to be centered on the load, whatever it is. And then you're going to basically go back to the fulcrum, say, where is it? And then this is going to be D out. So let's do a calculation for this lever. Okay, we're not going to take measurements. We're going to count blocks, okay? So we're going to count these blocks. So with D in, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Great. Out comes the calculator. Okay, so that's 11 blocks. So over here, I'm going to put 11 blocks. What is D out? 1, 2, 3, 4. So that's 4 blocks. So down here, I'm going to put 4 blocks, whatever the units were. If I'd done inches over inches, centimeters over centimeters. So what's 11 divided by 4? That goes into, oh gosh, I know this, 2.25. So that is the mechanical advantage for a first class lever. Find the fulcrum. Find where you put the input force. Find where the output force comes out. That's going to be the load, whatever you're lifting or moving. And then basically measure the distance from the fulcrum to each of those points. D in is fulcrum to input force. D out is fulcrum to where the load is. And what's the price we pay for this mechanical advantage? This mechanical advantage, distance. So you're going to have to push down, you're going to have to push down further than this thing comes up. Okay, there's always a price we have to pay. So any advantage we get in nature, well, maybe not every advantage, but in this case, certainly with machines, if you want more force out, you're going to have to put in more distance. Now we're going to talk about second class levers. How do you get the mechanical advantage for a second class lever? It's the same approach. Mechanical advantage is the ratio of the input distance divided by the output distance. So this is a second class lever. How do I know that? Well, because the fulcrum is over here, and this is my input force, and this is the output force. And so a second class lever, you've got the fulcrum, both the output force and the input force are on the same side of the fulcrum. Up here, we had, if you see, you can see the fulcrum here, we have the load, or the output force, is on one side and the input force is on the other. That's a first class. Second class, what we've done is we've taken the load and we have put it on the same side of the fulcrum as the input force. Okay, but how do you get the mechanical advantage for this? It's the same approach. What you're going to do is find your fulcrum. Let's see, let me try blue. Going to find the fulcrum and just think about, okay, where is it on the lever? Then it's the same. I'm going to make it a little tough. Then you're going to find out, okay, where are you pushing on the lever to make it move the load? Okay, well, here it is. Okay, so this is the input distance. It's the same approach as with the first class lever. The output force, figure out where that is. That's going to be basically the center of the load. This is going to be D out. So let's get the mechanical, and so it's the same calculation. It's the same thing. It's a little bit different lever, but it's still calculated the same way. So let's calculate it here. Let's count our blocks. So I'll just make a dot because you can't see my hand moving. What color do I want to use? Oh, let's use blue. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the input distance is 15 blocks. What's the output distance? Let's count. 1, 2, 3, 4, 5. Okay, so we got 5 blocks. Blocks cancels out, and we have a mechanical advantage of 3. So if you put in 100 newtons of force, you can lift a load that's 3 times as heavy as that force. So you could lift up 300 newtons, which is like 80 pounds. 70 pounds. 70 pounds or so. All right, that's it for a second class lever. What's the price you pay? Same as with the first class lever. If you want to get more force out of this lever, you're going to have to push down further than the load would be lifted. What's a classic third class lever? It is the wheelbarrow. I don't even know how to spell wheelbarrow. Okay, that's second class lever. Let's talk about third class levers. Okay, how do we get the mechanical advantage for a third class lever? It's the same process. So we're going to be, mechanical advantage is going to be D in over D out. Now what makes this a third class lever? Every lever is going to have a fulcrum. Every lever is going to have an input, which, okay, I'll say it basically is called effort. Probably in the gizmo it's called effort. And then there's going to be what I call the output, and maybe the gizmo is going to be called the resistance force. And what makes this a third class lever is, notice where the fulcrum is, and notice where the input force is, and notice where the output force is. Why isn't this a second class lever? On the second class lever, both forces were on the same side. Well, let's go back and look. Let's see. Okay, on a second class lever, if you look, the output force is closer to the fulcrum than the input force. Okay, so basically and that's the second class lever. look what's happening here, though, is now the output force, the load, is further away from the fulcrum than the input force. So they're switched. But the process to get mechanical advantage is still the same. All right, so let's figure out. Let's go through that same process. Where's the fulcrum? Okay, I think my fulcrum is, I'm still going to just, okay. That's a problem. I'm going to go back because things have moved. Let's go back. Go back. I don't want any motion. Okay, so I think I'm good now. Let's figure out where the fulcrum is. The fulcrum is here. Okay, I'm going to pretend it's actually right on that line for counting purposes. Just because it moved, the thing moved, and I didn't want it to move. All right, so basically there's the fulcrum. Here's the input. So this is our in, this is our F, and here's our out. Okay, so what's D in? Count the blocks. Okay, 1, 2, 3, 4, 5. Okay, so the input, no, I don't want blue, I want black. So the input is going to be 5 blocks. Goes on top, always on top. And the output, let's count. Well, I know that's 5. That's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, 15 blocks. Blocks cancel out as 1. And what do I get? I get basically 1/3. What? You mean I'm going to get less force out? A machine that gives you less force out than what you put in? What kind of machine is that? It's a very valuable machine. In fact, you have many of these types of levers in your body, which we'll talk about in a future lesson. But basically, so yes, you're going to get less force out. So it sounds crazy, but true. So if your load weighs 100 pounds, you're actually going to have to come up with 300 pounds of force. That's crazy. Well, let's make it a little more realistic. Let's make this like 10 pounds. And let's make this, so this will be 30 pounds. Okay, because you could do that. You could push up with 30 pounds. Why the heck would you ever want to do that? Well, for some reason, in this, a third-class lever, you're not interested in getting more force. You are not interested in getting more force out of your machine. What you're interested in getting is more distance. So if you kind of push up that far, you're going to get 3 times the motion. So a third-class lever, basically, what you're looking for is more motion than you put in. You're looking for a greater output distance than what you put in. And what's the price you pay? There's always a price you pay with machines, is you're going to have to put in more force. That's a third-class lever. It works the same calculation, all of them. So find your fulcrum, find your input, find your output. Fulcrum, input, output. And then measure the distance from the fulcrum to the input. That goes on top. Measure the distance from the fulcrum to the output. That goes on the bottom. That's how you get mechanical advantage of a lever. Doesn't matter which class lever.